In this video, we're going to look at the second part of functions. So this is going to look at some examples of graphs and using the vertical line test to test whether something is a function or not. And also we're going to look at evaluating functions when they're written in terms of an equation. So let's first look at a couple examples and determine if they represent a function or not. So to start off, we have this function, or let me rephrase that. We have this relation, and it's written as an equation, y equals plus or minus the square root of x, and that's representing these values here. Now, I did not draw this to scale. Okay, I did not draw out the square root of 0 is 0, so this point would be correct, and the square root of the positive or negative square root of 1 would be 1, so this point should be there and there, but this is just a rough sketch. To test to see whether this is a function or not, we would use the vertical line test. So if I can draw a vertical line through that green function and at any point hit 2 points and not just 1 point, then therefore that is not a function. So I'm just going to select right through here. I'm going to draw a dotted vertical line coming through, and you can see that that hits in 2 places. The green function hits that vertical line in 2 places, so we can say that no, this is not a function. Let's look at another one. Function or not. So on this function, it's the wavy line, we have a way to test to see if it's a function or not. So I'm going to take this and I'm going to draw vertical lines going down, kind of all the way through. Now, again, you could use your pencil to kind of go across and see if at any point it hits 2, but you can see it hits once, it hits once, it hits once, it hits once, it hits once. It doesn't overlap on itself, and this should be like continuous. I can't really show that with this method of drawing, but you would essentially be taking a line or a pencil and dragging it along the function to see if at any point it hits twice. I don't see any situations where it would hit twice, and so therefore, yes, this is a function. This represents a function. This next one, does it represent a function or not? Again, by the vertical line test, barring these arrows on the end, if I drag a vertical line all the way across that function that's drawn there, I see that each of these hits the vertical lines only once. Therefore, yes, this is a function. Let's look at one like this. The function is the kind of sideways V, and we have this point right here. If I drew a vertical line through that point, it hits exactly once. But if I shift over just a little bit, this would hit this vertical line in 2 places. So therefore, this is not a function. So I guess you could think of it as if it doubles up or loops around or even more than doubles up, then we would not have a function. So let's look at, I'm going to make up a new one. It's not on your actual notes, but let's look at this. So I have my coordinate plane. I'm going to draw this relation in green. So I'm going to draw this. Is this a function in green? Well, if I take a blue line and draw through it, I have 1, 2, 3, 4, 5 places where it crosses. So I can definitively say that no, this is not a function. Okay, is this a function or not? Well, does it pass the vertical line test? So we're checking to see if that red value, that red line represents a function. At no points on these vertical lines that I'm drawing does it hit more than once. So yes, this is a function. If I were to write this function, it would actually be written as y equals a constant value. So let's say that this was hitting at 4. Okay, so we would say that y is equal to 4, and that equation represents this line right here. Okay, and what that means is that for every value of x, y is equal to 4. So if I were to write that in a table, I would have my x values and my y values. My x values could be anything: 0, 1, 2, 1.5, 7, 1,000. What this function means is that no matter what my input is, my output is always 4. It's always a constant value. And so that's what my table would look like for a function like this. Let's look at this one. Now we have a vertical line. So if I were to impose a vertical line on top of this vertical line, would they have points where they interlap or intersect? And guess what? It's technically every point on this line. So this relation is not a function. Okay? If we were to write this as an equation, it would not be a function, but we could write an equation for it. We could say that x equals a constant. So whatever this value is, let's say it's negative, that was my cat, I apologize. Let's say this is negative 4, negative 1, negative 2, negative 3, negative 4. X is always negative 4, no matter what y is. So our table would kind of look like the opposite of the previous example. My x's are always negative 4 when I have this equation, no matter what my y value is. So for every x value in this, the x's get repeated and my y's could be anything: 0, negative 7, 100, 3. But my x values are all negative 4. It's kind of the opposite of what we just saw. Now let's look at this. This is function notation. Function notation is just one way that we write functions. Sometimes you'll see them written as equations, written like y equals 3x plus 5. This is a linear function. Okay, the input is whatever your x values are that you choose to plug into that, and actually it could be any value, and your y is your output or your range. Another way to write that, though, is to use this function notation. We say this as f of x, okay, and then you would say what your equation is, or what your function is. So we could rewrite this function as f of x equals 3x plus 5. But we don't have a monopoly on the letters. I could say I have f of x. I could also say I have g of x. And I could say g of x equals 7x squared minus 1. Okay? And all you're doing is you're representing a different function using a different letter. Because sometimes we'll have multiple functions that we're looking at. So we might have an f of x, a g of x, and an h of x. And so knowing that all three of those are just representing different functions will be helpful to understand. Now, the cool thing about the function notation is that this implies that we evaluate certain x values. So this is a function of x values, and this represents what our output will be when our input is x. Okay, when our input is x, f of x represents our output. So on our tables, we might write x and our f of x instead of x and y. But f of x just kind of replaces y. It means the same thing. What is our output? Okay, so this is why this is helpful, though. We can actually evaluate functions at certain x values. So when we're told f of x equals 3x squared plus 1, and then we're asked to evaluate f of 3, then what we do is we take the x value here and we replace it into our original function. So this would be 3, let me write the original. We have 3x squared plus 1, but the x here gets replaced by a 3, and I'm going to put it in parentheses so that we understand our order of operations. We're going to square the red 3 first, and then we're going to multiply that value by 3, And then to that we'll add 1. So our order of operations, remember, is parentheses, exponents, multiplication and division at the same time from left to right, and addition and subtraction at the same time from left to right. So we're going to start with that exponent applied to that 3. 3 squared is 9. And then we are going to multiply. 3 times 9 is 27. 27 plus 1, we end up getting 28. So we would say f of 3 equals 28. We can also do f of 0 and evaluate f of 0. So I can take my original function. I'm going to leave that open so I can plug in what I want to plug in there. We want to plug in a 0 where the x was. So we're going to do 0 squared, which is 0. So we end up with 3 times 0 plus 0. Well, plus 1. 3 times 0 is 0. 0 plus 1 equals 1. So we would say that f of 0 for this function equals 1. So when the function is evaluated with x being 0, our resulting output is equal to 1. So this is my output. So our f of 0 is equal to 1. 1 is our output, and our input was that 0. Okay, so let's look at some applications of this. We have this graph that represents a football being thrown by a quarterback to a receiver. The points in the figure show the height of the football in feet above the ground in terms of its distance, in yards from the quarterback. Use this information to solve the problem. So we have to be able to read the graph and interpret it. We also have to be able to read the labels and understand which one is representing what. So our x values are our input values. Those are our domain. So the domain is your x values, and it represents the distance of the football from the quarterback. That's this statement right here. So I'm going to kind of shorten that. So our domain is our x values, and it represents the distance of the football from the quarterback in yards. So literally, to answer that question, we just have to look at what is our x-axis and what is it representing. To look at the next question, it's asking identify the range. What does it represent? Well, the range represents our y values. Let me write that in red. That's our y values. What does it represent? Well, let's look back at the graph. It tells us the football's height above the ground in feet. When we look at the next question, we're finding the coordinates of point A and then interpreting them. So what that means is I'm going to look on this graph for point A. Okay, and look at our scale right here. This is in yards, so our yards skip by 3s. So this is between 0 and 3, so this value right here would be 1.5 is my x value for point A, and the y value is halfway between 9 and 12, which would be 10.5. So our coordinates for point A are 1.5 and 10. So we could say 1.5 yards, and the y value is 10.5 feet. And how we interpret that is we say that when the football is 1.5 yards from the quarterback, it is at a height of 10.5 feet above the ground. Let me say that one more time. At point A, the distance of the football from the quarterback is 1.5 yards, and it is a height of 10.5 feet above the ground. So we're using the labels in this situation to help us determine and interpret the different points on this graph. The next part we're going to look at is point D. Kind of mark, point D is right here on this graph, and it hits at the x-axis at 18 yards. Okay, so it's 18 yards away from the quarterback. And the height is at an interesting spot because the difference between these two values is by 3, 12, so 13, 14, 15. There's 3 units between there. And if you think about it, this is kind of 2/3 the way there. So if you think about it, this would be 12, 13, 14, 15. So D is actually hitting about at point 14. So how do we interpret this? We would say when the football is 18 yards away from the quarterback, that's our X value, it is 14 feet above the ground. That's our Y value. So functions model actual real day occurrences. Equations can represent the way things grow. They can represent things in our economy. They can represent interest, which is what we're going to see a lot of in this unit. They can represent a lot of real life situations. We're going to look at one more. I promise to try and keep it brief. Number 15 on the examples, I skipped a bunch because I don't want to spend forever on all of these, but number 15 is the function models the number of accidents, f of x, per 50 million miles driven as a function of a driver's age, x in years, where x includes drivers from ages 16 through 72 inclusive. The graph of the function f is shown. Use the equation for f to solve the problem below. So that's a lot of words to say this. We have an equation that represents this situation, okay? This function matches this graph. And what it's saying is that the function exists outside of those ages, but we're just looking at this part of the graph between 16 and 72. Okay, it wouldn't make sense to look at 0 years old because a 0-year-old child, which is like, I guess, born, like cannot drive a car. So we're going to use this graph or this equation to answer these questions. The first question is, what is the age of the drivers who have the least number of accidents? That point occurs right here. So the age of the driver who has the age of the drivers who have the least number of accidents is 44 years old. In a sentence, you would write, drivers who are 44 years old have the least number of accidents. What is the minimum number of accidents? In order to figure that out, we have to use the function. We're asking how many actual accidents do 44-year-olds have? And so that is our f of x value. That is our output. So we need to find out what is f of 44. Which means that in our function here, we need to replace all of the x values with the number 44. So we have 0.4 or 4/10 times 44 squared minus 35.2 times 44 plus 954 and 4/10. We can use our scientific calculator to calculate this. When we calculate this, we get 180.1 accidents. So for drivers who are 44 years old, the output of how many accidents they have is 180.1. Maybe it will let me type. There we go. Okay, so that is our answer to part B. I put it up here because I ran out of room, but this finishes up what we were looking at with functions. So a few key notes to remember is that functions have one output for each input. Functions have a domain, which are the x values, and those are the inputs, and they have a range, which is the y values, which are the outputs. A function can be represented as a graph, it can be represented as an equation, and we can also represent them as tables. They are used in real life to simulate actual situations that happen, and to model those situations is often the word that we use, model, math modeling. And then also these will show up to when we look at consumer math, because oftentimes things involving interest and compound interest and mortgages are based on functions. So knowing how to input a value into the function and evaluate it like we did in part B here is going to be very helpful. We're also going to see different types of functions like linear functions and quadratic functions and exponential functions. But that's a wrap up on functions. That corresponds to 6.10 in the book that we are using. If you have questions, please email me. And please follow up with the next videos on percents. Thank you.